Cool. So it's a great pleasure to me to introduce a speaker today, Karina, our own organizer, who will be talking about infinite family of triangles.
Hi, everyone. So yeah, as Willie said, I'm Karina. You probably know this. And today I'll be talking about my favorite theorem, which is Poncelet's Porism. So I originally gave this talk for the undergraduate math club at Stony Brook like 2 days ago. So the math will be hopefully pretty accessible for everyone. So sorry if it's a little bit basic for some of the older students. So yeah, just something to keep in mind. I won't be going through any sort of detailed proofs, and I certainly won't be proving Poncelet's Porism, as it involves some algebraic geometry that I don't know. So hopefully we can just have kind of more of a chill vibe on the math side of this. But I guess my goal for this talk is to provide some sort of intuition for what's going on with this theorem, and tell you also why it's so important to me personally. And so just to give you an idea of what I'll be talking about today, here's an outline. So I'll start by just describing the setting for the theorem and talking a bit about the theorem statement. And next we'll focus on a special case of the theorem involving triangles. And we'll spend a good part of the talk discussing an application to non-Euclidean geometry. So I'll introduce some things from non-Euclidean geometry. And finally, I'll talk about why this theorem has stuck with me as a definitive favorite over the years. And we'll look at some art that I made that was inspired by the Porism. Okay, so let us set up what this theorem is talking about. So we have the situation where we want to have two conic sections in the plane. So just for simplicity, I'll say that my conic sections are both just ellipses, because those are the easiest ones to draw. And so say that we pick some points on this outer ellipse. Maybe we want to start at this point or something. Then if you look into the inside, there are two tangent lines going through this point to the inner ellipse. So one of them is like that, and one of them is kind of like that. So I guess let's just pick this top line. And so we go through that tangent line and we intersect our outer ellipse again at this point. And so then there's another tangent line that we can follow from this point. And so we can just go along and go there. And we get to another point on the outer ellipse. So we can just keep repeating this process of just bouncing around from the outer to the, oops, it's a little hard to draw these on the fly. But anyway, we can keep going around and keep hitting points. And so we might find ourselves in the situation where we return to this original point that we started with, but also we might not. And so Poncelet's Porism is kind of talking about this sort of situation. So this is an example with just two ellipses, and I don't actually know if this will return to this point, but I drew some examples beforehand. So here are some examples of when they do return to our original point. So here's an example with just two circles, and we get a triangle between them. And here's one with like a parabola and a circle, and we bounce around a bunch of times, but we eventually close up. And it's also one with a hyperbola, which is also one of our conic sections. So some questions we might be having at this point is, when does this star-shaped thingy actually close up? So are there some conditions on the two conic sections that will ensure that we return back to our original starting point? Another question might be, how many times does this shape have to like bounce around before we do close? Or like maybe that number will be infinite if it never returns to the starting point. And also, what happens if we start at a different point? So maybe in this example over here, this one, when we start over here, it closes, but what happens if we start like at this point and go around? Like, is it also going to close? And if it does close, is it going to take the same number of bouncing? So Poncelet's Porism gives us sort of a partial answer to some of these questions. So let's look at the statement of the theorem. Okay, so it says, let C and D be conics in the plane. If there exists an n-gon P circumscribed by C and inscribed by D, then there exists an infinite family of n-gons circumscribed by C and inscribed by D. Furthermore, each point of C is a vertex of one of these polygons in the family, and each point of D is a point of tangent C. So I guess what this theorem is saying is that our takeaway is we either always bounce around exactly n times, or we don't close at all and we'll bounce around like infinitely many times. And also we can start at any point and get the same behavior. So not only can we start at any point on the outer conic, we can also start, say, like at the inner conic and be like, I want this to be a tangent point, and then just draw these lines and then bounce around that way. So, right. Okay, so this is what our theorem says. And I just wanted to give a little bit of historical context for kind of where this theorem came from, because it's just kind of interesting. So it was proven by Jean-Victor Poncelet, who was a French engineer by training. And he was also a lieutenant in Napoleon's army. So he invaded Russia in 1812. And yeah, I think the French actually got kind of wrecked by Russia. And so Poncelet actually got captured and he was a prisoner of war for 2 years in Russia. And while he was in jail, he proved this theorem. So he had a lot of time to think about math while he was in jail. So that's kind of a interesting story. But anyway, back to the theorem. So Poncelet's Porism gives us kind of like, if one thing exists, then infinitely many things exist. And I think that's sort of what Porism means. It's like a kind of theorem where you have that sort of behavior. But maybe it feels a little bit unsatisfying because it doesn't really tell you when our polygon actually exists in the first place. So I think in the general case, it's pretty hard to determine like conditions on C and D such that we have our infinite family. So for the remainder of the talk, I'll just be focusing on a special case. So this is the case where we let C and D not just be like any conic sections, but in particular, we want them to be both circles. And we're also going to want our polygon P to be just a three-sided polygon or a triangle. So this is the situation that we find ourselves in now. So I'll call C the circumcircle and D the incircle of a triangle. So our circumcircle, we're gonna call its radius big R, since it's like the bigger circle, and the incircle has radius little r. So in general, when we have a triangle, we always have an incircle and a circumcircle. So the 3 points of the triangle are non-collinear, so they define a unique circle in the plane. So that's the circumcircle, and the incircle is just the biggest circle that fits inside. So in general, these two circles are not going to have the same center. So I guess if our triangle is actually equilateral, then those two centers will coincide, but otherwise we're going to say that we have some distance, little d, between our centers. Okay, so in this case, we actually have a criterion which tells us exactly when C and D have a triangle fitting between them. And this is a result that we have from Euler. So Euler's theorem says that the relationship between the circumradius big R, in radius little r, and distance d for a triangle is this like polynomial equation. So it's d squared equals big R times big R minus 2 little r. So this is the relationship for like a three-sided polygon. And in general, I think we get from some algebraic geometry magic that if you're looking at instead a n-gon with circumcircle and incircle, the relationship between these three quantities is always going to be some sort of polynomial. So I don't actually know the details of why that's true, but that's just kind of cool. Maybe one day I will learn, but not right now. Okay, so now we can kind of reformulate our theorem in this special case. So I'm just going to call it our infinite triangle family theorem. So now if we have C and D being circles of radii big R and little r respectively, and without loss of generality, let's just take big R to be greater than or equal to little r. And let D be the distance between their centers. Then Euler's theorem basically just gives us this criterion that we know we have an infinite family of triangles, T alpha, circumscribed by C and inscribed by D, if and only if we have this polynomial relationship between the three quantities, D, R, and little r. Okay, so I have this picture that kind of illustrates what is going on. So I've drawn two circles, and because their radii and distances between the centers follows this relationship, we have an infinite family of triangles that fall between them. So I've drawn, well, a finite number of these triangles. And so, yeah, I kind of like how it looks like the triangles are just kind of like spinning around in there. And yeah, I guess if you look in Google, you'll probably find some neat GIFs of like the triangle actually turning around in here. So I guess at least from this picture, it looks like all of the triangles look sort of similar. So maybe we could wonder, are there any other similarities between these triangles other than the fact that they share the same inscribing and circumscribing circles? So let's look a bit at some examples. So this is the case when our triangle is equilateral. So in this case, we have that the incircle and circumcircle are actually concentric, so d equals 0. And actually in this case, so if we set the side equal to 0, that means that this side also has to be equal to 0. But r is always greater than 0, so that tells us that big R is actually 2 times little r in the case of an equilateral triangle. So in this case, all of the T alphas are equilateral. So if you draw any other triangle in this family, it's going to be, it's not a great triangle, but it's supposed to be equilateral. Okay, but in general, we're not going to have all of the triangles being the same. So if we look at this case, we've drawn 2 triangles in our family, and one of them is this pink acute triangle, and we also have this obtuse triangle, which are not similar. So I guess in the general case, the family of triangles are all going to be pretty not similar looking. Okay, so now I want to talk a little bit about how I actually came across this theorem for the first time. And this is also the part where we'll talk about some non-Euclidean geometry. So in the summer of 2017, I was doing an REU at Oregon State University. So there is me in 2017, and I was doing a project with Jacob Naranjo, who was another student, and we were advised by Professor Ren Guo. And so what we're doing is we were trying to generalize theorems from Euclidean space to spaces of constant curvature. So there are 2 types of curved spaces. You've got your positively curved spaces, which is in the constant curvature setting, this is just spheres. And then you have negatively curved spaces, which might look something like this. This is a hyperboloid. And actually the constant curvature negative space is called a tractricoid. So this one has negative constant curvature. And I guess this thing is also sometimes called the pseudosphere. So you've got your like sphere and your pseudosphere. So these were the spaces that we were like working on. And so, yeah, I just want to talk a little bit about what curvature is. So when I'm talking about curvature of these spaces, I'm talking about Gaussian curvature. So first, to define Gaussian curvature, we need to talk about what is the curvature of just like a curve. So let's say we're looking at this curve over here. And if we're looking at this point on the curve, we can consider the osculating circle at that point. So this is, I guess, the circle that most closely approximates the curve at that point. And so that circle is going to have some radius r, and then we define the curvature to be 1 over r. So a more kind of intuitive way of thinking about what this circle should be is like, imagine you're driving a car on like a curvy road on a really flat place. So in preparation for this talk, I looked up what the flattest state was, and it's actually Florida. which kind of surprised me. I don't know if there's a lot of big plains in Florida, but imagine you're like driving along this curvy road in Florida, and then at some point you decide to just like lock your hands in position and just hold the steering wheel steady, and then you're gonna drive around in a big circle, and then that is going to be the osculating circle at the point where you decided to stop turning the wheel. So yeah, so that's just a sort of intuitive way to think about what this curvature is. So I guess the reason we do 1 over r is that like if your circle is really, really big, then it's going to be kind of like flattish looking. So then the curvature should be smaller. But anyway, back to Gaussian curvature. So if we want to find the curvature of a surface, we do the following thing. So we look at all of these curves going through some point, and we can kind of define an orientation for the curve. So like a sign, a plus or minus sign. So the idea is we pick some direction for the normal curve, a normal vector. So it can either be pointing up or down in this case. So let's just pretend that we've chosen this to be our normal direction. And so I guess like this curve going through that point, since it's like kind of facing away from our normal direction, we'll say that this one is negatively oriented. And if you're looking at this curve with this normal vector, then we'll say that this curvature is positive. So then what we do is we find the curves of minimum and maximum curvature. So if those two curves happen to be like these ones, and they have curvatures K1 and K2, so this one maybe has curvature K1 and this one has curvature K2, then the Gaussian curvature is this product K1 times K2. Okay, so similarly, if we had these two being the min and max curves, then we do it like that. And so I guess in this case, both of these are negatively curved. So K1 and K2 are both less than 0. So at this point, the Gaussian curvature is a product of two negative numbers, so it's positive. And similarly, in this case, we have this one is positive and this one is negative, so then their product will be negative. And it turns out that it doesn't really matter which direction we chose for our normal vector. So like if we had instead chosen our normal to point the other way, then in this case, K1 and K2 would both be positive. So then the product will still be positive. So in the end, the signs all end up being okay. So these positively curved spaces are things that look kind of locally like little bowls. And in the negatively curved cases, I guess we call them the hyperbolic cases, they look more like the Pringles. So the two curves are like going in the opposite direction. Okay, so how do we do geometry on these spaces? So let's talk about the spherical. So since we're on a sphere now, we can't really have like straight lines anymore. So we'll look at the geodesics as our lines. So if we choose, say, 2 points on the sphere, then the line between them is going to be the great circle. So these are like the lines that are, or the circles that are equators. And so using this definition of a line, we can still have triangles on the sphere. So triangles look sort of like this pink triangle. And yes, there's a question in the chat. Is Gaussian curvature only for planar manifolds, or does it exist also in higher dimensions? I actually don't know. I would hope that it generalizes, but I've actually never thought about curvature on higher dimensional spaces, but I'm sure someone else in this talk knows. Right, so I was talking about spherical triangles. So we also can have circles on the sphere, which are just like the set of points on the sphere that are equidistant from some chosen point. So our spherical triangles can also have these circumcircles and incircles. And so I guess if you look at this triangle, it looks sort of like it was like inflated a little bit. So we can also measure angles on a sphere, and we just define the angle to be the angle between the tangent lines. So I guess the kind of result of this is that at each corner of the triangle, it's going to be like slightly made bigger. And so when we take the sum of the angles here, we're going to get something that's bigger than pi. Whereas if we're just working on a flat plane, then the angle sum should just be equal to pi. So our triangles look sort of a little poofier in spherical space. And okay, so now we can talk a little bit about hyperbolic space. So there are a lot of different models of hyperbolic space. So I thought I would talk about just a couple of them. So one model is the Poincare disk model, which is a conformal model, meaning that the angles you see in the picture are actually what the angles should be, like, yeah. So they don't get distorted at all. And so the Poincare disk model says that our hyperbolic space is defined to be this, like the interior of this disk, and our geodesics are arcs of circles that are perpendicular to the boundary of this disk. So these ones are arcs of circles, and also we can also have these like infinite radius circles, which are just the diameters of the circle as well. So we also can define circles in hyperbolic space, and we do that by defining some sort of metric on this space, and then the circles are the points that are equidistant to some central point. I don't remember the metric offhand, but it has something to do with logarithm. So I guess the basic idea is that distances near the boundary of the disk get like really, really big. So we can think of this boundary line as being like the line at infinity or something. So these distances are actually like really, really big, and these ones are like more smaller. And I guess it's a little bit hard to see in this picture since my triangle is so small, but actually all of the corners of the triangle are like slightly pinched because we're using circular arcs instead of straight lines. So it turns out that the angle sum of our triangles in hyperbolic space is always going to be less than pi. And I guess you can sort of think of curvature intuitively as like how much less or greater than pi the angle sum of a triangle is. So for more curved spaces, it's going to be like further away from pi. Okay, so there's like, I don't know, like 5 or something different models of hyperbolic space. But there's also another one called the Klein model, where we model our straight lines as just being straight lines. But this model is not conformal, so we do get some sort of distortion from the angles. So these angles are not actually accurate. And also our circles get sort of distorted as well, so they'll look more like ellipses, and they'll get more distorted as you get towards the corners of the disk. But yeah, I guess the benefit of this model is that you can just draw straight lines, and so it's maybe a little bit easier to draw than these. So the different models are, I guess, useful in different cases. So yeah, so that's just a brief introduction to some non-Euclidean geometry. So, right, let's bring it back to some stuff that we were talking about earlier. So you remember this Eulers formula in Euclidean space. So this was this d squared equals r times r minus 2 little r. And so something we could wonder is, what about in spherical or hyperbolic space? I guess for spherical and hyperbolic triangles, is there a generalization of this formula? So it turns out if you just apply this formula as it is in spherical and hyperbolic triangles, it doesn't hold. So I guess what I was trying to do in my RU was find a more general version of this that holds in spaces of positive or negative curvature. So this was one of the problems that I was working on with Jacob. And so what we did was we started by working in the isosceles case. So when our triangle is isosceles, like 2 of the sides are the same length. So that kind of removes a degree of freedom, so it becomes a little bit easier to solve. And we were able to come up with this kind of unifying formula for the quantities d, big R, and little r. And so in the spherical case, we had to do something with signs, and in the hyperbolic case, we do the same thing, but with hyperbolic sign, or sinh as it's sometimes called. So I guess the Eulers formula looks a little bit different from what we had before, but if you like factor it out and rearrange it, it ends up looking like that. But anyway, so we were able to prove that this is true in the isosceles case. But we were getting pretty stuck on doing the same thing for a general triangle. So we weren't sure that this same formulation would hold in general, or maybe we're missing some like invisible terms that cancel out when you have an isosceles triangle or something. So this actually brings us back to Poncelet's Porism somehow. So let's talk about that for a second. So first of all, Poncelet's Porism actually holds in spherical and hyperbolic space. So just a kind of quick way of thinking about this is that if you have our triangle on the sphere, we can look at the projection onto the tangent plane at, say, like the incenter or something. And so we project onto the plane using stereographic projection. And the nice thing about stereographic projection is that geodesics on the sphere get mapped to straight lines in the projection, and also circles get mapped to circles. So when we project up to the tangent plane, we get basically just the case of a Euclidean triangle. So just a triangle in the plane with circumcircle and incircle. And then Poncelet's Porism holds up here. So then we can like move it to any other triangle in the family up here, and then also project it back down to get a triangle with that like starts at any point down on the sphere. So you can do something similar for hyperbolic space using the Klein model, but I won't really be talking about that in any more detail than that. Okay, but anyway, the important thing to take away is that we can use Poncelet's Porism even if we're not on just a flat plane. Okay, so a corollary of this is that if you have a triangle T with circumcircle C and incircle D, then there exists an isosceles triangle T prime with the same inner and outer circles. So just a kind of proof sketch here. So if we have our just general triangle T, then it has its incircle and circumcircle. And I guess if there's no distance between the two centers, then your triangle is equilateral. And in that case, it's already at least, I mean, it's better than isosceles in that case. So we can assume that there's some distance d between the two centers. And then we can look at the line between those 2 points. So it's going to intersect the circumcircle at 2 points. So let's just pick this top point over here. And by Poncelet's Porism, we can make a triangle starting at this point that is in our Poncelet triangle family. And just by like a symmetry argument, this triangle will be isosceles just from the way that we set up the construction. So this gives us that if we have a triangle, that we're always going to have some isosceles triangle in the family of triangles that are between these two circles. So what that gives us is that the formula that Jacob and I found together actually held in general. So since it holds for isosceles triangles, it also holds for these general triangles, because you can just like shift it to the isosceles case and then have this relation hold for there. And then since D, R, and R are not changing as you go back to your original triangle, it's also going to hold for T. So yeah, this was one of the first like research results that I helped to find. So I guess that is all the like mathy stuff that I wanted to talk about. So I also wanted to talk about, for the end part of the talk, a bit about what I feel about this theorem, because I really like it. and maybe for some reasons that are not quite obvious yet. So I guess just to recap what we talked about, because we talked about a lot of things. We talked about Poncelet's Porism, and also how we can use this theorem to understand more about triangles in spherical and hyperbolic space. So to close the talk, I wanted to talk about why the theorem resonates with me on like an emotional level. So I feel like sometimes that as mathematicians, we can sort of get caught up in the more technical aspects of our work, like the definitions, the theorems, the proofs. And something that I don't see math people talking about very much is like why they do what they do. Like what drives us to do math, even when it's frustrating and difficult. And also, how does the math that we do make us feel? And so for me, Poncelet's Porism is a reminder of the why. So let's look at this drawing of some triangles. So during my REU, aside from doing research, we were also presented with an additional challenge, which was to design a t-shirt for the REU, which is also a very important job. So since I was spending most of my time with Jacob studying triangles, I somehow came up with the idea to draw all of the REU students as their favorite triangle. So I already knew what my favorite was. It was this one, the hyperbolic triangle. So that's supposed to be me as a hyperbolic triangle. And so I went around and asked everyone what their favorite triangle was. And I came up with the design that you see here. And yeah, so we made a shirt, and I'm actually wearing the shirt right now. I don't know if it's kind of hard to see, but anyway, it's basically just the drawing that you can see better on the screen right now. So this shirt has become something of like a lucky math shirt for me. And sometimes I'll wear it like on exam days for extra good luck. So anyway, because of this design, I had already been thinking of myself kind of like as a triangle and like as my friends as triangles too. And I guess the context is we were nearing the end of my program, and Jacob and I had found the generalization of Eulers' formula for isosceles triangles, but we were stuck on extending this to like the general case. And so what happened was a few days before we were supposed to present our results, our advisor tells us about Poncelet's Porism. So I'm sure he knew this all along, but just like wanted to see what we could come up with on our own. But anyway, the theorem statement that he provided with us looks sort of like this. So it said, every triangle has an infinite family of triangles that share the same incircle and circumcircle. So we saw this statement, and he probably drew a picture that looks sort of like this. And it was at that moment when I first read this statement that something kind of like clicked for me. And I guess it wasn't only because this gave us what we needed to complete the proof, but it felt kind of comforting when I read the theorem. I guess it was this idea of an infinite family of triangles. And I think it was because this sort of seemed to mirror the feelings and experiences that I was having in the REU. So just for a bit of like context, I had never really felt confident in my mathematical abilities. So this was in college, and I was like pretty average as a math major at Harvey-Mudd, and I was always like surrounded by these brilliant people who seemed like they were like on a different level. than I was. And like, even when I applied to this RU and I was accepted, I felt like I didn't really deserve it and that I only got it because I got really lucky somehow. And not only was I insecure about my abilities to pursue math seriously, I also never felt like I was part of the mathematical community at large. That was something that had always kind of eluded me. But during the 8 weeks that I spent in Oregon for the RU, I felt for the first time like I actually belonged in the mathematical community. So I got along really well with my research partner, Jacob. We're still friends. Actually, he's the one who's with me in my like Facebook profile picture because he came to visit me one time. And yeah, in the RU, all the other professors and students were all really cool, and I felt like we were like our own little community. And so to bring it back to Poncelet's Porism, the fact that all triangles exist in an infinite family felt like metaphorical in light of all the things that I was experiencing. So like the triangle was me, and my infinite family was the math friends that I had made. So yeah, I realized that this sounds maybe kind of cheesy, but that's just what I was thinking at the time. So the next semester after this summer, I was taking like an intermediate drawing class, and that basically just meant that we're like allowed to draw whatever we wanted to, which is cool. So even months later, I was still thinking about Poncelet's Porism, and I wanted to make a drawing that explained how I felt about it. So I'm gonna show you the drawing. It's kind of like a long drawing, so I'll just like kind of scroll through it slowly, and then we can talk a little bit more afterwards. Okay. Okay, so this is basically a wall scroll that I made out of paper, and it's about 4 feet long, and all the people here are people who basically just encouraged me in my mathematical journey over the years, and people who I felt like were a part of my mathematical family. And so the words that are a bit illegible in the picture are just things that each of them had told me that really encouraged me. So here's just like a close-up of the figures and drawing. So there's Jacob and there's me. But anyway, yeah, I feel like maybe it's a little bit strange to talk about like my feelings and my art in like a math talk, but I guess these are all things that I wish that people felt more comfortable discussing in the math community. And I guess I've been thinking lately about like what makes a like a mathematical contribution meaningful. And I think usually the things that we as a community put like value on are like our theorems and our papers and books and stuff. But I guess for me personally, like even though I've co-authored papers and done some research and stuff, this drawing feels like one of the more mathematical works that I've done that feels like meaningful, at least to me. Yeah, I guess I think that like my math-inspired art is a part of who I am as a mathematician just as much as all those other things. So that's why I want to try and talk about them together more often. Yeah, so I guess my hope for the future of the mathematical community is that we can learn to be more welcoming and also open to talking about the more personal and human side of math that I think at least draws all of us to pursue this field. So yeah, that's all of what I wanted to talk about today. So I just want to thank you for listening and also say thank you for being also a part of my like infinite math family. So yeah, I guess we can have questions but that is what I wanted to talk about for today. So thank you.
Great talk.
Thank you.
Thanks very much, Karina. All right, so any questions or comments, anyone?
I have a question that is sort of about the theorem. So Poncelet's Porism says that, if there's one triangle, well, then there's an infinite number of these triangles.
Right.
And maybe this is obvious, but I mean, are there also points where it won't be a triangle? In the case where there is at least one.
Right. So in that case, the Porism tells us that no matter what point you start at, you're always going to close and also close in 3 steps so that you're always going to get a triangle that's circumscribed and inscribed by the circles and not like a quadrilateral or higher thing.
Wow.
But you could not have any sort of aperiodicity, like if there's one per like if I think of it in terms of dynamics, right? If there's one periodic point, then all the points must be periodic.
Right.
Right, and like we can kind of think of this procedure as defining a map from like from S1 to itself, right?
Right. I think it definitely has something to do with dynamics. I think you could view it in that kind of perspective. Yeah, I think the proof of the theorem actually, there's probably a lot of different proofs, none of which I can understand at this point, but they involve like elliptic curves and some AG things. So maybe if you looked at the proof, it would like show a little bit more about the like dynamics of the situation.
Because like if I think of it like from a dynamical point of view, like I'm used to thinking about like it's a very common problem in dynamics to study maps from the sphere to itself, like from S1 to itself, and then like what can happen, how bad can it get? And the answer is it can get really, really bad. And somehow here we have a sub collection of maps where once we know that there's one periodic point, then we know all the points are periodic. Like that's kind of, from a dynamical point of view, really exceptional. Yeah, sorry, that wasn't really a question, more like a comment to what I thought about.
Oh yeah, that's definitely cool. Like I'm sure there's a lot of different perspectives that you could look at the results from.
I think usually what people call it is billiards. So it kind of looks like, billiard trajectory if your table is like a circle or something.
Yeah.
And then, like dynamics, they do use some algebraic geometry as well to like generalize like the sort of like study, I think, if I'm not wrong. I've barely heard of it, but I think it's quite interesting.
Yeah, I heard of those billiard problems as well, but yeah, very interesting. Thank you for a good talk.
Thank you.
All right. Any other comments?
Maybe this is just because I don't understand English, but is it clear why it's called porism? I mean,
Yeah, so I think porism is like a weird word that no one really knows what it means, but like, I don't know, I think it comes back from like Euclid used it or something, but I think it's basically the way it's used now is like, it means a porism is a theorem where like, if you have one thing, then it guarantees the existence of like an infinite family sort of thing. So I think there are also some other porisms, maybe like Steiner's porism. Can't remember any other porisms off the top of my head. But yeah, it's not really a word that's used very often anymore.
right.
Karina, are there any like applications of the porism other than like, I mean, it's cool, it's really cool, but like, are there like, did you, when you were like reading on it, was there like anything like, I don't know, it looks like this is very like out there, but there are like different types of like, I know that there are types of like flowers that like look kind of like this, and I don't know, I just think I'm just like wondering if there's like anything anything in relation, like applications of this. I don't know, people that have, I don't know.
Yeah, I guess the answer is I don't know if there's any like more like physical applications.
That's okay. I just,
Yeah, I don't know. It's interesting.
cool. Like I've seen crochets, I've seen like embroidered crochets with this, and I'm just like,
Right.
if there's like a way to do it in like simpler steps, like using this, I don't know. I just,
Yeah, I'm sure you could use it to like construct some really cool like string art sort of things where you like draw all these straight lines, but then it looks like it's curved when you look at all of them together. Yeah.
cool. Thank you.
All right then. Thanks very much, Karina.
Right.
So
Nice
the
talk,
next
Karina.
talk will
Everyone.
be Tim. He's going to talk about, well, something next week. All right. Okay. See you guys. Have a good weekend. Bye-bye.